Ever find yourself reading something long, maybe a report or even just a long article, and you get to the end and realize you can't quite recall the specifics from the beginning? It's like your brain just overwrites things.
Oh, absolutely. That feeling is, well, it's actually a pretty good analogy for a big challenge in artificial intelligence, especially when dealing with lots and lots of information in sequence.
Right, like processing huge documents or following a really complex story over time. How does an AI hold on to all those crucial details?
Exactly. And, for a while now, transformer models have been the go-to solution. They're incredibly capable at understanding context.
But they come with a cost, right? Computationally speaking. Especially when the sequences get really, really long.
Precisely. They can be quite demanding. And that's opened the door for alternatives like linear sequence models. They're designed to be much more efficient.
Okay, efficiency sounds good. How do they achieve that?
Well, the core idea is they compress the entire input sequence down into a single fixed-size memory state. Think of it like a running summary.
Okay. Faster processing, I get that. But I can already see the potential problem. One single summary for everything.
You got it. That compression, while efficient, creates limitations. How much can you really store? And what happens when new information comes in? Does it mess up what's already there? That's called memory interference.
Okay, so that brings us to the main event for this deep dive. We're going to get into a newer architecture called Mixture of Memories, or MoM.
Yes, and the goal is really to understand from a more, let's say, academic perspective, how MoM tries to tackle these exact memory limitations in linear models. We want to focus on what's truly innovative about its approach.
And we're basing this on our research notes, and crucially, the actual paper titled MoM Linear Sequence Modeling with Mixture of Memories. So we'll be digging into the details presented there.
Exactly. Getting into the nitty-gritty of the design and the evidence.
Perfect. So let's start with that core problem again. Why is it so fundamentally hard for these linear models to remember things accurately over long stretches?
It really boils down to that compression into one single state. Imagine, like you said, summarizing an entire complex novel into just one sentence.
Yeah, impossible. You'd lose all the subplots, the character details. It would be a mess.
Precisely. And the MoM paper explicitly calls this out. It talks about limited memory capacity. You just can't fit infinite detail into a fixed space. And crucially, memory interference.
Interference, like different memories clashing.
Exactly. New information, essentially overriding or corrupting older, potentially still important, information stored in that single memory state.
The paper brings up that quote from neuroscientist David Eagleman, doesn't it? Something like, the enemy of memory isn't time, it's other memories.
Yes, and that quote perfectly captures the essence of the problem MoM is trying to solve. It's not just about holding information for a long time. It's about keeping distinct pieces of information separate and accessible, preventing them from blurring together.
So if interference between memories is the main enemy, how did the MoM researchers approach designing a defense? Where did they find inspiration?
This is where it gets really interesting, academically speaking. They look towards neuroscience, specifically how the human brain, particularly the hippocampus, manages to store and retrieve multiple memories without them all getting jumbled up.
The biological approach. What about the hippocampus caught their eye?
Well, the paper discusses the role of brain waves, these oscillations at different frequencies. You have the slower theta waves, around 4-8 hertz, and then much faster gamma waves, like 3100 hertz.
Okay. Different frequencies. How do they relate to keeping memories separate?
So the theory, and this draws on work from people like Buzaki and Lisman and Jensen, is that within one cycle of the slow theta wave, you can have multiple cycles of the faster gamma waves.
Right.
And each of these quick gamma bursts might activate a different small group of neurons representing a different piece of information or memory item.
So it's like time sharing. Briefly activating one memory, then another, all within a short window.
Exactly. It's a form of temporal segregation. By activating different neural assemblies at slightly different moments, the brain potentially keeps those memory representations distinct and prevents them from interfering with each other.
That's fascinating. A biological mechanism for avoiding interference.
And that core principle separating memory items to reduce interference is the absolute key inspiration behind the MoM architecture. The researchers essentially asked, can we build an artificial system that mimics this idea?
Okay, a brilliant leap. So how is this principle actually implemented in the MoM model? What are the core architectural innovations here?
The absolute foundational innovation is the use of multiple independent memory states, instead of that single compressed summary state we talked about. MoM uses several distinct ones. Think of having, say, 4 or 8 separate notepads instead of just one crowded one.
Okay, more notepads means more space, intuitively. But how does the model know which notepad to write on for any given piece of incoming information? You can't just scribble randomly.
Good question. That's where the second key innovation comes in, the router network.
Router network sounds like it directs traffic.
Pretty much. For each input token, like a word, the router calculates an importance score for each of those independent memory states. It essentially asks which memory notepad is most relevant for this specific piece of info.
And then,
Then it uses a mechanism technically involving something called top K selection and a softmax function to pick a small number, the K most important of those memory states.
okay.
And only those selected memory states get activated and updated with the information from that input token. The others remain untouched for that step.
Ah, so it's selective updating. That seems crucial. It's not just having more memory, it's intelligently routing information to specific memory locations based on relevance.
Exactly. This selective activation is a core differentiator. It's not just simple gating. It's a mechanism designed specifically to keep different streams of information segregated, directly tackling that interference problem inspired by the neuroscience.
Okay, makes sense. And what are these individual memory states themselves? What's inside the notepads?
Each one is what's called a linear recurrent memory module. But here's another academically interesting point. MoM isn't rigidly tied to one specific type of linear recurrence.
Meaning?
As the paper shows in a table, you can plug in various existing linear recurrent update rules, things like LA Lightning, RetNet, HDRN2, Mamba2, GLA, others too, into these memory slots.
So the innovation isn't necessarily a brand new way to update a memory, but rather the system of having multiple memories and the smart router managing which ones get updated when.
You've got it. The architectural framework, multiple states, plus the router is the primary contribution here. It's a system-level innovation for linear models.
Got it. So the relevant memories get updated. How does the model then bring that information together to, say, answer a question or predict the next word?
Through a step called memory mixing. The memory states that were just activated by the router are combined.
How? Just averaged?
Not quite. They're combined using a weighted sum. And critically, the weights used in this sum come directly from those important scores the router calculated earlier.
Ah, so the memories deemed more important by the router contribute more to the final mix.
Exactly. This creates a mixed memory representation that blends the relevant information from the activated states.
And that mixed memory is what the model uses for its output.
Yes. A query is then applied to this mixed memory to generate the output, which then goes through some standard processing like normalization and activation functions. The paper details RMS norm and swish, for instance.
Okay, that covers the core selective memory part. But the paper also mentions something called a shared memory. What's that about? Is that another innovation?
Yes, it's presented as an additional complementary component. Think of it as a way to capture more global context.
How does it differ from the independent memories?
While the independent memories are updated selectively based on the router, the shared memory is updated continuously with every single input token the model sees.
So it's like a running tally of the overall context alongside the more specialized selective memories.
That's a good way to put it. It captures the broader picture, the long-range dependencies across the whole sequence.
And how does it get used?
Its content is integrated with that mixed memory we just discussed from the activated independent states before the final output prediction is made. So the model gets both the fine-grained, selectively stored details and the overarching context.
Interesting. So it's a combination of selective, specialized memory, and continuous global memory.
Precisely. Both contributing to the final output.
Now, the name mixture of memories, it immediately makes me think of mixture of experts, or MoE, which is a pretty well-known technique. The paper tackles this comparison directly, right?
Yes, absolutely. Appendix A goes into this because the names sound similar, but they address fundamentally different things. It's a crucial distinction.
Okay, so from an academic angle, what's the key difference in purpose?
Mixture of experts MoE is primarily about scaling up model size, specifically the number of parameters, while keeping computation manageable. It usually involves having many expert networks, often in the feed-forward layers, and only activating a few for each input.
Right, making huge models practical.
Yeah. MoM, on the other hand, is laser-focused on improving the memory capacity and reducing interference specifically within linear sequence models, which are already aiming for efficiency. The goals are different.
So MoM is about scaling compute and parameters, often in transformers, while MoM is about fixing the memory problem in linear models.
Exactly. And structurally, they differ too. Mo experts are typically separate networks. Mo memories are distinct recurrent states within a linear recurrence setup, each with its own projection weights. And operationally, Mo often routes tokens to experts, somewhat independently, sometimes called channel mixing. MoM routes information relevant to sequence segments to memories, more like token mixing, preserving sequence flow within the activated memory.
That clarifies things nicely. Different goals, different mechanisms, even if the mixture of naming is similar. Okay, let's talk results. How did MoM actually perform in experiments? What's the evidence?
The paper shows a pretty comprehensive set of experiments. They looked hard at what they call recall-intensive tasks. Think question answering, finding specific facts in text tasks where remembering accurately is key.
And the results there.
Really significant improvements compared to other leading linear models. And importantly, at the 1.3 billion parameter size, MoM was getting performance close to much larger transformer models on these recall tasks. Table 2 in the paper lays this out.
Close to transformers on recall. That is significant for a linear model. What does that tell us?
It's strong evidence that the architecture really is boosting memory capacity and, crucially, mitigating that interference problem we keep mentioning. It's doing what it was designed to do.
Okay, impressive on recall. What about other language tasks, like reasoning?
They tested on common sense reasoning benchmarks too, things like predicting sentence endings, choosing plausible continuations. Table 3 shows MoM consistently got the best average score among the linear models.
Better than other linear models, okay.
And, interestingly, even outperformed transformers on some of those specific tasks.
Wow, a linear model beating a transformer on reasoning. What's the implication there?
It suggests MoM isn't just storing facts better, but perhaps its way of organizing and accessing information also aids more complex reasoning processes, which is a really compelling finding for an efficient architecture.
Definitely. And the big test for linear models, long sequences, how did it handle those? Transformers struggle with cost there.
They used the long bench benchmark. Table 4 shows MoM performs strongly, especially in few-shot learning and code completion within long contexts. It suggests the architecture scales well and maintains its ability to track dependencies over long distances.
So it seems to hold up across different challenges. Now, you mentioned the core idea is multiple memories are better than one big one. Did they test that directly?
They did. A crucial ablation study, shown in Table 5, they compared the full MoM with its multiple mixed memories against a baseline model that had just a single memory state, but they increased the size of that single state so it had the same total capacity, same number of parameters as all the MoM memories combined.
Ah, a direct comparison.
And the MoM approach, multiple separate mixed memories, performed significantly better. Just making a single memory bigger wasn't nearly as effective as organizing it into multiple managed states.
That really nails the point, doesn't it? The structure of the separation is key, not just the raw capacity.
Precisely. It's strong empirical validation for the core architectural principle inspired by that neuroscience idea of segregation.
And did all these improvements come at the cost of efficiency? Did it lose the linear model advantage?
No, and that's critical. The paper emphasizes MoM retains linear time complexity for training cost, grows linearly with sequence length, not quadratically like standard transformers. And inference computation per token is constant. Figure 2 illustrates this.
So you get the memory and performance boost without sacrificing the core efficiency benefit.
Exactly. It aims for the best of both worlds.
Just quickly, did they look at training dynamics or fine-tune the number of memories?
Yeah, briefly. Figure 3 suggests MoM had lower training loss, potentially learning more efficiently. And paper 6 explores things like the number of memories finding, for instance, that 4 memories with 2 activated per step was often a good balance. They also confirmed the shared memory component significantly helped on those recall tasks.
Okay, so wrapping this up, what's the big academic takeaway here? What does MoM represent for the field?
I think MoM is a really innovative advancement, specifically for linear sequence models. It directly confronts their historical weak spots, limited memory capacity, and interference. By cleverly using multiple memories managed by a router, inspired by how the brain might work, it achieves a much better balance between computational efficiency, which linear models are known for, and strong performance, especially on tasks needing good recall where they previously lagged. It's a significant step.
It really sounds like a promising direction, this idea of a sparse solution, as they call it, that doesn't brute force the problem, but uses a more structured approach.
Absolutely. And the neuroscience link provides such a different angle on designing these systems.
It makes you wonder, this multi-memory idea, separating information to keep it clean, where else could that be applied? Beyond just language.
That's the million-dollar question, isn't it? Could you use similar principles for AI and robotics, needing long-term spatial memory perhaps? Or for agents navigating complex environments over time, needing to recall diverse past experiences without getting confused? It definitely opens up avenues for thought.
A fascinating possibility. Well, for anyone listening who wants to dig even deeper into the technical side or see if there's code available, we will definitely put links to the paper and any repositories in the show notes. Definitely seems like research worth watching.